I think it would be good to step back a little bit and think sort of on a broad picture how galaxy formation happens. So basically the way if we think of a coarse-grained view, right, we coarse-grain everything on some large scale, then we can think of the matter that forms a galaxy, or that we then observe at, oh, this thing's dying, that forms at some, that doesn't form at that time, but we observe it here, forms along this fluid trajectory, again, in a coarse-grained sense, leading back into the initial conditions. So I denoted this as XFL of tau. And it's clear that this formation happens over long time scales, the history of the universe, many Hubble times. But we think that the spatial region over which galaxy formation happens is fairly restricted, right? So if we think of a halo of some mass, then it assembles mass within of order the Lagrangian radius of the halo, right? So that's the basic picture, right? We have this tube-like region, as I always imagine it, narrow in space, but long in time. Right. So then, in this coarse-grained view, well, so in full generality, we should write, if we want to do a bias expansion, or in general describe the abundance of galaxies as a function of space and time at some final point, is some function of the local gravitational observables along this fluid trajectory, right? In this tube-like region, right? And I'm saying only gravitational observables because now I'm neglecting any feedback type of effects and saying, okay, they don't matter on sufficiently large scales. That's, of course, something worth discussing. So the local gravitational observables are completely captured for the Newtonian regime by the second derivatives of the potential, right, di dj phi. And so if we go on really large scales so that we don't have to care about the finite region within which this mass is assembled, then this becomes a local function in space, right? Think of a very long wavelength perturbation that's approximately constant over this shaded region. We can treat it basically as just evaluated on the fluid trajectory, but we have to evaluate over the entire fluid past history, right? This is because this formation happens over a long time, right? So we end up with this nonlinear functional of di dj phi, but it's only a functional in time, not in space. Okay. That's basically the picture on large scales. And now, how do we turn this into a bias expansion? Well, basically, we expand this function of di dj phi into all scalar combinations, and the number density of galaxies is a scalar. Then we get the matter density perturbation squared, tidal field squared, and so on, all nonlinear combinations. But in addition, we need to expand this time integration. And so for each operator in this list of density squared, and so on, we have this kernel that we can sort of do a formal Taylor expansion in terms of derivatives along the fluid flow, right? So these are not coordinate time derivatives, but convective derivatives along the fluid flow. So, okay, this, at first sight, this doesn't help us at all, right? Because given that this is a long period of evolution, this doesn't converge, right? This time derivative is not any smaller than basically the delta prime, right, is not any smaller than delta itself in some sense. Right? But we can make the use of that we know the time evolution of each of these guys in perturbation theory, right? So for example, just consider delta itself. The linear first order perturbation theory just scales as a growth factor. Second order scales as second order growth factor, or simplicity linear growth factor squared, and delta d cubed, and at higher orders, and so on. And so if you go to some fixed order in perturbation theory, right, you have a finite number of terms in the series, and that means there's only, you can take arbitrarily many time derivatives, but they are eventually linearly dependent, right, because you only have a finite number of terms in this expansion in time, right? So it's a little bit of a subtle point, but yeah. So basically, sorry about this. This is my one technical slide. So you can basically use this fact, right, that at any given order in perturbation theory, you only have a finite number of different time dependencies appearing in delta. You can use that to reorder the bias expansion. And for example, think of this pi1 as just being di dj phi, and pi2 being some time derivative of pi1 of di dj phi, and pi3 second time derivative. So on. In reality is some linear combination, but not so important. Then you can write down just a list of all the terms we need to include in the bias expansion. So trace pi1 is just the density. So this is the well-known linear bias, right? At second order, we have density squared and tidal field squared, the famous BS squared, or by now famous within this room, let's say. And then you have at third order, you have density cubed, all combinations. And then at third order, for first time, a time derivative term appears. And then at fourth order, you have several of these. You have a cube, third time derivative type, and second time derivative squared, and so on. So you can see there is, the number does increase fairly quickly with order and perturbation theory, but there is a finite set. And the nice thing about this type of order, this type of expansion, is that you can either think of it in a Eulerian way, where you directly can read off the usual density and tidal bias parameters, or you can work in Lagrangian space, where you think of pi ij as the derivative of the displacement with respect to Lagrangian coordinate, and the same thing, the same type of basis can be written down. So this basis does not care whether it's Eulerian or Lagrangian biasing. There's no difference anymore. They're basically two different bases in this full vector space. And then there is, of course, stochasticity also, which is important. So at linear order, you just have one stochastic field, but at second order, you have another stochastic field multiplying the density, and so on. So stochastic parts are also add to the numbers that we need to include. Okay, so there was, of course, one major caveat here, because I kept talking about the large scale limit, right? Now, if we go to sufficiently small scales, at some point it will matter that galaxy formation is not completely local, right? It actually happens over some non-local scale, which I've denoted here with this gray region, right? So there is some scale, which I call R star, within which galaxy formation depends in detail on the distribution of matter, right? And so in the perturbative treatment, what you do is you expand the, now you have like a functional in space as well, and you expand that functional, and again you get all, so you expand the functional, that leads to higher derivatives of the density field and of all other bias parameters, and then you do this expansion in derivatives. And the key point is that each of this higher derivative comes with a scale, right? It's not dimensional, it comes with the scale, which is basically governing the non-locality of galaxy formation. So at first order in perturbation theory, you would have R star squared Laplace delta. And then second orders, you have a ton more. You have grad delta squared. You have, this is just examples. So you have Laplace of the tidal field squared, and so on and so on. And this then leads, right? So this, if you Fourier transform it, it leads to a scale-dependent bias with some scale, k squared R star squared, right? Well, okay, yeah, excellent question, right? So if you observe, so this I presume is an early type galaxy, I guess. It looks like it, right? So right, this could have, you have better eyes than I have. So of course galaxies form due to merging, but presumably the progenitors come also within some finite region, right? But so if you had some, no, So they're also, so all the merging is governed by, what I assume is that all the merging is governed by gravity, right? And so that is all taken into account in the expansion of the, I mean, the merging probability and whatever you could think of is all governed by the tidal field and the density, right? Local density. And if it really, and probably it would also depend on derivatives of the density, it will depend on the curvature of the density field, for example, and that's exactly this guy, right? Now, of course, there is radiation effects and feedback effects, and in general, they should also have some scale, R star, associated with them, right? So if you say a gas gets blown up to 10 megaparsec, so maybe then this scale would be associated with the feedback would be a 10 megaparsec scale. There are worse cases, for example, if you have the Lyman alpha forest, which depends on the local UV background, right? And the UV background cares about basically the entire Hubble volume at that time. So then the scale could be huge for Lyman alpha forest. So that will be a worrying case, right? Because the perturbative description basically completely breaks down because of this additional scale, right? So, oh yeah, I wanted to add one slide on assembly bias. Well, I just Googled scatter plot and then looked for a plot with blue and red points. So this is actually, you know, some Raman spectroscopy of cancer treating proteins or something. Anyway, so the key point I want to make here is, so basically, you define your sample of galaxies. It will define one point in this high-dimensional parameter space of bias parameters, right? So B1, B2, B3, and all the other ones I listed, right? Higher derivative ones. You know, you define your sample. There's one well-defined physical set of bias parameters, and that, of course, depends on time. So, you know, your galaxy will do a trajectory in this high-dimensional space, and yeah. So I think the key part is to include all of these bias parameters to ensure that these actually have physical meaning, right? So in principle, the bias parameters multiplying all these coefficients have a proper meaning if you include all of them, right? If you include drop some of them, then you will get, you will generally bias your result. But yeah, so just as another example of, yeah. Actually, I don't have included plot, but yes, my student measured B4. B4 exists, yes. Maybe for peaks, but certainly not for galaxies, right? Yeah, but density to the fourth is, yes. Right, but actually Marcello makes a good point, which is that if you have some, you could well imagine that now you take, you know, you define some criterion for identifying subhalos, for example, and do that with many different parameters. I mean, or do HRD with many different parameters, and you will, in this higher dimensional space, they will define some locus, right? They will fill up some region, and there will be correlations between the different bias parameters in general. And maybe that could tell us something, and that could help us basically put priors on the relation between bias parameters when we constrain them with data. So I think there are some interesting correlations in this higher parameter dimensional space, but from a purely, you know, just saying, I mean, so basically what I described, just assume the equivalence principle in Gaussian initial conditions. And if you just assume that, then in general, all these parameters will be there, right, and free parameters. And you need additional physical assumptions, peaks or, you know, HRD types to put any constraints on the relation between them. So basically, to recap, what I wanted to say, essentially in a nutshell, is that we now know which bias parameters have to be included at any given order in perturbation theory, including the higher derivatives and stochasticity. Especially those latter two I think, are incompletely understood, and there's a lot of room to make progress there. And of course, also, I should point out that for any given statistic at a given order in perturbation theory, many of them can be degenerate, right? So Urot already mentioned this B3 and L, which is a combination of cubic bias parameters that completely determine the autopower spectrum. So the second part of my talk will be basically a little bit on addressing this well-defined question: what are these biases for dark matter halos? Not splitting by formation time, even though we could do that, and I think would be quite interesting. And so I will focus on the local density bias, again, this trace pi to the n and the basis I described. But maybe some questions so far on this first part before I move on to somewhat disjoint second part. Yes, so there's two things. So there's actually three things, right, that limit our reach in K. So the first thing is just our description of the underlying matter field, because these relate. It's the matter field and tidal field, right? Right. Okay, I agree. The second issue is that, of course, if you have some large bias parameters, they can lower this scale, lower the perturbative reach, because, say, you have some nonlinear correction that comes with a cubic bias, and that cubic bias is 50, then, of course, whereas for matter it's 1, then, of course, your perturbative reach will be smaller. And the third scale is this nonlocality, right? And I think this is really a fundamental limit, in my view, because at this level, you know, all these things like subhalo distribution within their parent halo, and all this stuff, you know, halo concentration and determining what the distribution of galaxies within a halo is, and all that will contribute at this order. So I'm very skeptical that we can rigorously control in any way these higher order terms. So this is basically the third cutoff. No, so there's, of course, there's order unity coefficients for sure here, yes. Yeah, I mean, I think for mock catalogs, right. I mean, it depends on what you want to do with the mock catalog, but in general, it would probably be better to use some kind of HOD stuff, which is fine. I mean, what you can do is you can generate mocks that have the same biases as you see in the data, for example, right? Even though they are generated in a complicated nonlinear way, you can adjust the knobs to make them have similar. I mean, first thing is make sure that the mock galaxy live roughly in the same halos and so on. I mean, that can get you pretty far. But okay, so basically, I mean, this is sort of more of a discussion topic, but I think we have to, I mean, if we really want to extract cosmological information in the sense of constraining W and constraining FNL and these things, I think we have to restrict ourselves to scales where we can put a rigorous theoretical error bar. And to me, that is only guaranteed in the perturbative expansion. So, you know, but there's, of course, tons of information on smaller scales, but I would be hesitant to claim anything about, you know, fundamental physics from those. But of course, this is a discussion topic. We should discuss this. It's my opinion. Strong statement? Well, yeah. Well, yeah, the background, but the background is very easy to include here, fortunately, right? But I agree, we assume GR, right? So one has to, if you want to look for modified gravity, then one should also include the, yeah, breaking of the equivalence principle in principle, yes. So I have no idea how much time I have left, but. Okay. So let me talk about a nice measurement of local bias of halos. So going back to, this goes way back in time, right, when we were still measuring local bias of halos, that my student Titouan Lazera has been doing. So basically the way we do this is we use this separate universe approach. So if you have a long wavelength density perturbation, then you can locally, it's indistinguishable in GR from a curved universe with different values of omega m, omega lambda, and h naught. And I want to emphasize that this is exact, not only at the linear order, but at nonlinear order. So, so what we did was just simulate a range of simulations with varying long wavelength density, and then take the derivative of the mass function with respect to that long wavelength density, and that's the bias parameters, right? So we, and actually because we do this to nonlinear order, we don't just get B1, but you get B1, B2, B3, B4. So let me start with B1. Sorry, a little bit busy plot, but the overall trend is, of course, low mass halos have close to 1, and high mass, this is Eulerian bias, have a much higher bias. The green points are from the separate universe. The red points are from halo-matter cross-correlation that Tobias did. And then we compare to Jeremy's fit of the bias to simulations from 2010 and various other approaches that we can discuss. I don't want to spend too much time on it here, but you can see what tiny error bars, right? This is sub% level errors on B1. Good, so I think it's, right. Yeah, Tobias is still working on the, on fixing those. No, but this is still work in progress, but, sorry? Yeah, that's the red error bars, right? Green for the separate units. Yes, we have several realizations. So, of course, we do cosmic variance cancellation. We compare, for different delta values, we compare the same initial conditions, but we do this whole thing for many realizations. B2 is probably more interesting because there are fewer measurements so far and much less precise. And so there we compare with BHMM, for example. Yeah, I mean, again, it's, these errors are now at the few percent level on B2. So I think it's kind of neat. One should also say that they are, of course, the different biases are correlated, right? The error on B1 is at the same mass spin is correlated with the one on B2 because we're fitting a polynomial. And B3, there the error bars get a little bit bigger. But I mean, it's interesting that all the standard peak background split approaches still do, you know, they get within 20%, let's say, even for B3. So it's kind of interesting, but and even the overall trend, right? Positive at low mass, then turning negative, and eventually becoming positive again. So anyway, so this was just a neat, kind of cute little thing I wanted to show. And yeah, so one could also do this with the other tidal field biases, scalar dependent biases, and so on. So stop here. Thanks.